Thank you very much for the invitation to speak to this group. I was able to come to the first talk, and then as I was telling Les, I'm now teaching a big second-year class of 150 students where we're teaching thermodynamics in a compressed form in just 7 weeks to 150 students. So I've been kind of busy in addition to having a fourth-year course. So it's nice to be able to take a break and come here and talk about hopefully sustainable energy. What I'm going to do is give sort of a big picture talk of the energy issue, and I'm going to talk about how we currently use energy and then see what some of the challenges are, and there are many, in trying to make that use more sustainable. I think, and there probably aren't many engineers in the crowd, so I can be a bit harsh on my colleagues in the profession, I guess, in that engineers tend to be detail driven. Some of you may know engineers, and you know we like to really drill down and get deep right away, often too early. And I'm always telling students, before you do that, it's really important to do that because you have to get the details right, but before you do that, you need to stand back and really try and look at the big picture, get a big picture view, and then you can go from there and dig down. And unfortunately, I think in society generally, we hear whatever today's latest solution to the energy crisis is, and it's somebody who's drilled down to their particular favorite issue, and they haven't really stood back and understood the complete picture. So that's what I hope to be able to do in this presentation. So here I've got a lot of material, and I'll go through it pretty quickly, but if there are questions, it's a nice small group, just shout out, and I'll try and answer them as we go along. So I'm going to talk a little bit about the energy problem. I don't think I need to say much about that to this group, but just by way of background. I'll then introduce what I call the energy conversion chain, which I think is the key issue in taking a big picture look at how we're currently using energy, and importantly, how we might do a better job of that. And then some of the real challenges in moving to a more sustainable system, and I'm going to zero in on one of those, sustainable transportation, I guess because A, I'm personally interested in that issue, and B, it's a really difficult issue, and primarily all powered with fossil fuels. And then sort of a summary of where we might be able to go in the longer term. So the problems are, and again, I don't need to say much to this crowd about that, but global warming due to our contribution is, of course, CO2 emissions from burning lots of fossil fuels. And today, 80% of our total energy comes from fossil fuels. So 80% of all the energy we use in the world comes from fossil fuels. And the issue I think that's often forgotten is that most people really like using energy just as we do today without ever thinking about it. They like to plug their laptop in and not worry about, you know, if there's coal behind that outlet that's generating the electricity they're using to charge up their laptop. Most people like to get in a vehicle and have the freedom of being able to drive wherever they want to go. And so I think that's a big issue, and I'm not going to say too much about that. I'll again take a sort of a big picture view. Well, many of you probably know this global carbon cycle, and so this, you know, standing back, this is where a lot of the carbon goes. So very big picture view, we've got fossil fuels here, and the units are in gigatons of carbon, not gigatons of carbon dioxide, but gigatons of carbon. So we've got a lot of that stored here in the earth, and of course we're digging that up continuously and pumping it out and using it in cars and to heat our factories and run our businesses and so on. And as a result of that, we put about 6 gigatons a year up into the atmosphere. And then some of that is accumulating, but only about half of that currently is accumulating in the atmosphere. It turns out that, of course, and there'll be many here probably know a lot more about this than I do, there's an exchange, of course, between that CO2 in the atmosphere and vegetation of about 60 gigatons a year, and another exchange between the atmosphere and the ocean of 90 gigatons a year. So in sort of round numbers that engineers like to use, we've got 150 gigaton exchange here that's more or less in balance, and we're putting up the 6 gigatons over here. And so there's a little bit more being accumulated than we're putting up. So that means that we're sort of putting a net 3 gigatons up in here, which is plenty. The point I make on showing this, however, is that what we're doing here is clearly very important, and that's what I'm going to try and address here, but these natural exchanges are very important as well. And if something, you know, a little perturbation in one of these, which might ultimately be triggered by what we're doing here, could be very bad. It could be better as well in some situations, but we just don't know that. There's just too much uncertainty, I think, in that. Okay, so let's get back to what we're doing. Well, here's CO2 emissions up till 2007 in the United States, and I picked that because the biggest economy in the world, I think still at the moment anyway. And here the units aren't terribly important, but now there's megatons of CO2. The energy business is one where people use different units all the time, so you have to be sort of multilingual in this, but the units aren't terribly important. But what it shows is where CO2 emissions have gone from 1990 up till 2007, and you see steadily increasing up and down a little bit as the economy goes up and down, of course. And then the red bar down here is the Kyoto target that the US would have had if they had signed on to the Kyoto Agreement. So they were meant to be, if they'd signed this, down to this level by a little bit further than here to where we are now, 2010, 2012. And I haven't got more recent data on here, but it just continues to go up like this. So you see the challenge when we're doing this to get down to a level like that. That's the data for the US. Of course, we're Canadians, right? We're here. We're a lot smarter than that, right? We do a much better job. So here's the Canadian picture. Look how good we're doing, right? You could just overlay these, like most things you can do in comparing the two economies, one over the other and divide by 10. That's essentially what this is. We're just going up just as sharply here. Glitch down here as the economy goes down and so on. And here's our Kyoto target, which we did sign on to, down here at 6%. And I guess we're still going up here. So you can see, I don't know what's going to happen when we finally end up here. I guess the government is saying, well, they're going to pull out or something like that. I don't really follow the politics of it, but you can see that we're not going to achieve this target, and no one is going to achieve the target. What's that? You said we're out of Kyoto. Yeah. Have we actually done it? We actually said we're out? Okay. So, all right. Well, I'll move on from that slide then, because, but the point I'm trying to make is I think nobody else is going to make those sort of targets either at the moment, the way we're going. So that brings me then to the more engineering part of this, and this is the energy conversion chain. And I said to Les that I wasn't going to say anything about thermodynamics, no equation certainly, just that energy is conserved. So you do know that, I'm sure. Energy is always conserved, but what we're doing is always converting it from one form to another. And we start with very few primary sources, and of course we want to convert that into a form that's more usable for us. And I think I told Les I wasn't going to use the word entropy, but here it is in this slide. And so if you, like I do, teach thermodynamics, you know that really there's no such thing as sustainability, right? It's not a sustainable world. Entropy is always increasing. Entropy is not conserved. Everything we do increases entropy in the world. So I won't go any further than that in the philosophical argument, but we might have some discussion afterwards. So let's get back to the energy conversion chain. Well, it starts at the end point down here, and this is where we use energy. So we use energy, and I think every use we make of it, you can put in very broad terms in one of these four categories. So we use it to power our cars and subways and airplanes and so on, power industry, and heat and light commercial and residential buildings. And I think every time energy is used, it's for one of these four end uses. And all of that energy ultimately comes from one of only three energy sources. And there are only three primary energy sources. And they are, of course, fossil fuels. 80% of this comes from fossil fuels today. Nuclear energy and renewable energy. So broad categories, but that's where the energy comes from. And every bit of energy we use down here has to ultimately come from one of these three primary sources. So the chain is just linking that up. So we take a primary source here, and we typically do some processing of it. So we take the fossil fuel, so let's take crude oil we pumped out of the ground, we process that in an oil refinery, and then we end up turning that into a carrier. And there are only three carriers that are used today. And they are here, petroleum products, so the gasoline has been formed from the primary source here. Natural gas has a little bit of processing just to remove sulfur and that kind of thing from it. And electricity is, of course, an important energy carrier, and it's generated from one of these primary sources, typically fossil fuels, nuclear energy, or, of course, in this province, pretty much all from renewable energy. So that's a good thing. But after that processing, then, we just have these three carriers. But I've got hydrogen here with a question mark. because that's a potential carrier. It's not, as a lot of the newspaper articles would have you believe, a source. It's simply a carrier, and it has to compete with these other carriers. And I'll go through that in an example, and we'll see why that really isn't a viable carrier at the moment. And in my view, after this analysis, I hope you'll agree it's probably not likely to be. After that, we take a carrier, and often we like to store the energy. So the gasoline we've got up here, store in the fuel tank in your car, and then finally there's an end-use conversion step which takes that stored energy and we use it, again, using the car example, the gasoline goes in the engine in your car, generates a lot of entropy as it's doing that, but it provides you with motion down the road. And so these little arrows here are meant to show emissions of pollutants as well as, of course, CO2 in many cases here. So in general, there are emissions here as well as in the end-use conversion step. And so there's lots of CO2 comes here from the final step of using fossil fuels. So this is the energy conversion chain, and I like to use that and get students to take a look at that, and I think everything they do from an energy point of view, everything you do can be pictured on a plot like this. Okay, so that's by way of background, and now I'm going to spend most of the time, I guess, talking about some of the challenges from where we are today. And I'm going to go through just a few of them. I mean, I've got a lot more in a much longer talk, but some of the ones I think are really important. Clean coal, and we hear this all the time, you know, clean coal. And it sounds like an oxymoron, doesn't it? So we'll spend a few minutes doing that. And then I'll look at renewables and then at nuclear power. So some of the primary sources. And again, clean coal is just one component, or coal is one component of fossil fuels, which today provide 80% of our energy. Well, oxymoron, well, I chose this as a deliberately provocative slide, and I hope there's nobody from the Canadian Coal Association in the crowd. No? Good, because I'd probably just head for the exit right away if there was. But you know, I think this is what people tend to think of when they think about coal. This is a pretty dramatic picture. I just kind of like that. More realistically, if you don't know, this is what a coal-fired power plant looks like. And about 40% of the world's electricity is generated with coal. Only about 17% in Canada, so we're doing much better than the rest of the world, but 40% of electricity comes from coal. And people see this and they say, oh my goodness, this is just terrible. First of all, if you don't know, this is only water vapor. These are cooling towers, so there's no pollution coming from these devices. Lots of people, my poor wife included, think that this is terrible pollution. When we drive around quite a bit in the UK, she sees this and freaks out, and I try and convince her that's just water vapor. This is where we've got pollution. Here's the stack, the chimney here, and all this that you see is water vapor as well. When you burn fossil fuels, of course, you end up with water in the products, and that condenses and causes, but within that, there's also CO2 and some other pollutants in there. So a major source, of course, of CO2 production from coal-fired plants. This typical 2,000 megawatt is about the typical size of a big electrical power plant. Now, can we do a better job? Well, yes, we can. There's something called, and sorry if you don't know the jargon here, this is IGCC, is Integrated Gasification Combined Cycle. That's kind of a mouthful, but what it basically does is takes the coal and gasifies that. It's a very old process that's well known, well established, but turns it into gas first of all. And if you have a gas, you can then run a gas turbine. And so you can run that at a much higher temperature than you can a steam turbine. And then you generate some electricity with that. You take the heat that's left over from the gas turbine, you use that to generate steam, and then you run a steam turbine as well. So that's the jargon, integrated gasification combined cycle. Combined cycle means you're combining a gas turbine and a steam turbine. The benefit of that is it increases the efficiency significantly. And the gasification, there's some other advantages along with gasification, and it's somewhat less polluting than burning the coal directly. But the benefit is really through the increased efficiency of this. But you're still producing a lot of CO2. Better efficiency, you're producing less CO2 than a conventional plant. But these still are only in the early development stage. So they're only relatively small test plants. This is one down in the States in this. But if we're going to burn coal, this would be the way to do it. You're going to have, I know, a really good talk in a couple of weeks, I think, from Professor John Grace in chemical engineering on carbon capture and storage. And I'm just going to touch on that briefly, basically with a few slides here. He will talk about the details of that, but that's one of the things that folks, of course, particularly in the coal business, say, well, what we're going to do is we're going to capture this CO2 and we're going to put it underground and get rid of it that way. So, that's okay. There's just conventional engineering processes that enable you to do that. Capturing the CO2 is not technically a problem. The problem is the sheer volume of it. There are just huge quantities of CO2. And if you have to have equipment that intercepts large volumes of material of any kind, it's expensive. That's the problem. And it uses some energy to do that. So every year we produce, worldwide, something like 22 billion tons of CO2. So that corresponds to the 6 gigatons going up of carbon only. So roughly 22 gigatons of CO2. And if you take this at standard temperature and pressure, that's something like 12 times 10 to the 12 cubic meters, which you see is 12,200 cubic kilometers, and a volume 23 kilometers cubed. That's the amount of CO2 we're producing. That's what we got to store underground. Now, if we do this, we're going to pressurize it. We're going to compress it and put it underground, so it won't be quite the big volume. But even if you put up the pressure of 10 bar instead of 1 bar, for example, you're still going to have a humongous volume required to store this stuff. And then, is it going to stay underground? I mean, there's all these issues with it. So it's one of these solutions, if you like, which, yes, it's possible, but there's so many challenges with it. And of course, doing this is not cheap. And there have been quite a few estimates looking at what the cost might be to do this, and it essentially doubles the cost of electricity generation from coal, for example, to do this, is what most of the estimates seem to indicate. People are already doing this in a really fairly small way. CO2 injection has already been used by the people in the oil business for some time to actually enhance the recovery of oil from existing wells. So what they do when the oil starts to get harder to pump out of the ground, they'll drill a well behind a production well. So this is a production oil well here. They'll drill one down here and pump down CO2 and use that to push some of the oil and gas and so on to the production well and back out again. Then they'll separate the CO2 from the product at the end here. So this has already been used, is being used fairly extensively. And then these are the various schemes that have been proposed for storing carbon underground, sequestering carbon sequestration is what some people call it. So you've got to say a coal-fired power plant here. Well, you could put that down into old coal beds. Coal is very porous and will absorb a fair bit of CO2. You could put it in old oil and gas reservoirs. That'll probably be the first place that would be used if this would go ahead. Or people said, well, we'll put it down and dissolve it in water in these deep saline aquifers. The idea being if there's saline, nobody's going to want that water in the future anyway, so we can put it down there. And the Japanese in particular were quite keen to just dump it in the ocean. But there's lots of people who are not so keen on that, so that's probably a non-starter. But these are the possible ways that this might be done. And it's being used now and tried in Norway. This is the Sleipner natural gas field. And what they're doing is they're taking gas from much deeper down in here and bringing it up. It turns out that the gas has got a pretty high CO2 content with it. They don't want that, so they separate it out on the platform and put the CO2 back down in this sandstone formation here. And they're putting it back in there. So that's from one production well. They weren't really doing it, I don't think, to save CO2 emissions. They're doing it to kind of clean up their gas. And there have been a number of demonstration projects, and there's one in Canada. I mean, Canada has an IEA project in Saskatchewan where CO2 is being taken from a facility and it's actually being piped down to, I think, South Dakota and being injected underground there. But very small scale pilot plants. Again, there's lots of monitoring going on and so on, but you need to make sure if you're going to do this, I think, that it's going to stay there for a very long time. Okay, enough about that. Let's move on and talk about renewables. Well, we hear that's the panacea. We're just going to change to renewable energy. So That would be nice. And I won't talk about all of these, but these are in no particular order, I guess, the sort of general list of renewable energies. And pretty much all of them ultimately, if you go back the energy conversion chain, are due to the sun, right? So the sun energy is responsible for the energy that we take in the form of renewable energy. And almost all of these, I think. Combustible renewables and waste, folks in the forest industry know all about that. That's hog fuel that you're burning in boilers, and I guess that ultimately has come from the sun growing trees and all that kind of thing, as is wind energy, you know, all of this stuff, with the exception of geothermal energy. That's the one, I guess, that we can't attribute directly to the sun. So here's a list of what's possible to use. What we make use of course, is significant amounts of this and significant amounts of hydropower and relatively small amounts of the rest. And so we can use wind, of course, and many of you will know this nice wind farm off Denmark. Denmark has been one of the leaders in using wind turbines to produce electricity. Solar energy, there's lots of different ways to do that. You can convert it directly to electricity using solar cells. And this is out in the, I think in the Mojave Desert and the US Department of Energy. 4.6 megawatts is a significant amount of energy put out there. Have had this experimental plant for a long time. And then there's another way that you may know of to utilize solar energy to generate electricity without using photovoltaic cells, and that's by a conventional steam power plant that's down in here. And here these mirrors, these heliostats they're called, are steerable. They follow the sun and they collect the sun's radiation and focus it up on the top of this tower here, and then you circulate water through there, generate steam, and run a steam turbine, right? So this process where you take this mirror and focus it, this is just like you know, when you were a kid, you may have taken a mirror or something and shone the sun on your baby sister's leg or something until she screamed, right? It's that same kind of process. But it's done, and now there's a 10 megawatt plant. So again, these are getting bigger in scale. There's some advantage to that. The next evolution of that is, again, steerable mirrors. These are now parabolic mirrors in a row like this. So, and they steer to follow the sun across like this. And then at the focal point here, you can see there's a pipe runs along here, and then the pipe contains water. And that's then turned into steam and goes off to a central plant and generates electricity. And you get a feel for the scale by the people in here, right? So again, if you've got lots of desert area like they have in California, you can do this. Now there's a 150 megawatt plant. So we're getting serious scale here. And I have to say at this point, you know, I kind of slagged the Americans off at the beginning, and they get a lot of knocks in this business for not doing anything. They have spent far more money, serious money, building big demonstration plants like this than anybody else on the planet. And so they're showing what could be possible. The trouble, of course, with most renewable energy sources is they are intermittent. Right? Sun doesn't always shine, wind doesn't always blow, and particularly wind power. And people get very excited about wind power. And the folks who sell you wind turbines will never tell you that the number they quote you, 3.5 megawatts for their wind turbine, only operates at that capacity about 30% of the time. Right? So the capacity factor, we call it in the business, is very low. The capacity factor of a coal-fired plant or a nuclear plant is about 90%. You might expect it to be down 10% of the time for maintenance. But you're only going to get something like 30% of the rated capacity out of a windmill for you know, a year's time. So that means it's intermittent. Of course, the solar plants are intermittent in nature. And so you either need some kind of backup power, and that kind of defeats the purpose. If you put in 100 megawatts of wind power and then you say, well, gee, but I've got to have 100 megawatts of coal-fired plant standing by, that's an incredibly expensive type of backup power to have. So that's very expensive. It would be really nice to have some way of storing electricity. All of these plants are generating electricity, right? So it would be nice to store electricity. Well, turns out that Canada is in pretty good shape in this. We have one of the world's biggest batteries. And, you know, I used to give this, I've been giving this talk for quite a while, and I would say, you know, in BC we have the world's biggest battery. And then some smart guy came down from the back and said, you know, I think there's a bigger one somewhere else. So I had to go back and do my homework. Turns out we've got the world's third biggest battery here. And when I say battery, it's just water stored behind a dam. That's probably the most cost-effective way to store large quantities of energy. So you see here Williston Lake is the third biggest battery in the world. The bigger one is Lake Volta in Ghana and Manicouagan in Quebec. I was disappointed when I did this research to see that Quebec's got battery twice as big as we have, right? And this is the installed power generating capacity associated with each of these devices. But the big issue, and I think people don't realize even in BC, the real advantage we have here is not so much our generating capacity, it's the storage we have. So we have this very large storage facility. And this is it. This is the Shrum Dam, if you don't know this, or I guess it's, yeah, the Bennett Dam and the Shrum Generating Station. That's what it is, up on the Peace River. And this is Williston Lake behind it. So this is a big battery. This is a very large storage reservoir. And I'm sure I don't have to emphasize to this crowd what I'm always surprised I have to tell engineering students, that Williston Lake is the biggest lake in the province. I'm sure everybody here knows that. Many engineering students, and my own kids, for example, don't know that the biggest lake in the province is a man-made lake, right? And I guess I've been around long enough that when I was a boy, we went on holiday up to watch this dam being built and them start filling up this lake. So there it is. If you don't know where it is, Williston Lake, I think it's 500 kilometers that way and 250 kilometers here to Hudson Hope, where it abruptly comes to a stop at the Bennett Dam. So that's the kind of storage device we have here. That means if we had some of these intermittent sources, we could use our storage facility to store up that if there was excess energy. And because we just close off the hydro gates and we don't generate electricity from that, then when the wind stops blowing, we open those gates again and generate electricity. Now, hydro, of course, already uses this storage capacity very effectively, at least cost effectively, because what they do is just through arbitrage, they buy in, and I don't think we should be proud of this necessarily, but they buy in power from Alberta, coal-fired power at 2 a.m., say 2 a.m. to 5 a.m. in the morning. If you're running a coal-fired plant, you don't want to shut it down, right? It's not very good for it to shut down. They like to run them all the time. So the power gets incredibly cheap in the middle of the night when people aren't using power. There's always a small residual amount of power. So what BC Hydro does is essentially shut down the generating capacity here, buy that power from Alberta, use that for our needs, and then the next day at 6 p.m. they open the control gates on the dam and generate as much power as they can and wheel that down to California. So you'll know our transmission lines go down to California. And they made 1 year $1 billion doing this, just pure arbitrage. But they made that amount of money because of the storage capacity we have, right? So the storage is very important. They use it for different reasons than I would like to see it used now to support other renewable activities, but it's very important to have that. Okay, nuclear power. Let's have a look at that. Well, I like this picture of, some of you will recognize this is, I guess, the biggest nuclear station in Canada. Something like 16% of Canada's electricity is generated with nuclear power, primarily in Ontario and Quebec. And this is the Pickering plant, which is just east of Toronto. So it's probably an example of the biggest nuclear plant in the world next to a very large city anywhere in the world. And I kind of like this plant because you see this little token windmill down here, that this, when the wind blows, this might generate a megawatt. It is a 4,000 megawatt plant, and it'll do that probably 80% of the time. So I kind of like this picture. But, you know, there are issues with nuclear power. You don't have to believe me. You just need to read the newspaper about this to know that it's expensive. Safety, of course, is an issue. Waste disposal is an issue. But the biggest issue associated with all that is really public perception, right? It's what people think of nuclear power. And whatever I might say as an engineer, if I'm a nuclear engineer, I probably will be in favor of this, and I say this is wonderful and it generates no CO2. If I can't convince you and everyone else in the world that this is a reasonable way to go, we're not going to build more nuclear plants. Now, not everybody in the world thinks that way. France is a society that on the technical side is kind of run by engineers, I'm pleased to say. So where do they get their electricity? Whoops, I've gone too far here. Okay, maybe I'm going to come to that in a minute, and I think this might be out of sequence. But so before I get to that, I hopefully will come back to that. This shows the cost. So I did say cost is one of the issues. And the cost here, this is from a study a few years ago now from MIT, but they did a pretty exhaustive study. Both a group of engineers and economists got together and really looked at what a new build nuclear plant would cost in terms of electricity production. This is including all the costs that would be required for waste disposal and everything else. And it's here about nearly 7 cents a kilowatt hour, right? To put that in perspective, if you're not calibrated, we pay about 6 cents a kilowatt hour for our residential electricity here in BC. Okay, so you would probably have to double that from a plant like this for anybody to make money and pay for the distribution and so on. But much of the rest of the world, of course, has electricity rates like that. We have, I think, the world's cheapest electricity here. It's incredibly cheap. And then I've put some other plants on here. This is PF coal is pulverized fired coal, so pulverized coal plant here with the orange bar. So this is with no carbon price attached to it. This is a combined cycle gas turbine, the most efficient way to use natural gas to generate electricity, and it's down here, a little more than half the price. And so if you didn't have any other incentive, you would want to probably use a gas turbine to drive that. It depends on the cost of gas, of course, and I had looked at this a few years ago when the cost of gas was actually $12, $15 per, this is million BTUs or 1,000 cubic feet of natural gas. It's now about $2, and it's not going anywhere because we're finding more and more gas. So very cheap to generate electricity with gas. And then I just took those numbers, and here's, as the gas price goes up, you see the price goes up for the gas generation till pretty soon, even at $9, it's the same price as nuclear. If you put, and I put $100 a ton of carbon, so there's a very nominal carbon tax on top of that and just added it on. And if you did that, the cost of a coal plant would be the same as a nuclear plant, and the cost of gas as the gas price goes up gets higher as well. You see, the tax is much bigger on a coal-fired plant because the CO2 production is about twice from coal as it is from gas. So it does put the cost in perspective. Yes, nuclear is expensive, but if we're serious about carbon, we want to do something with these other things, then it will be a cost-effective supply.
Decommissioning cost in there as well?
Yeah, they've put decommissioning costs in. I mean, who knows how accurate they are, but if you look at the study, everything is included in that. Okay, I go back, I think, now and talk about my French colleagues and to say, I've only heard this secondhand, but I've been told that France is run by graduates of École Polytechnique if they're in the technical side, and by the Sorbonne if they're on the economics and humanities side, and that's how the world works. So as a result of that, 80% of electricity in France is generated with nuclear power, right? And you look, this is a pretty nice pastoral scene, isn't it? This looks pretty nice. There's no pollution here. That's water vapor. Remember, I told you that the first slide. So no CO2 emissions. You've got these lovely sunflowers growing here. What a lovely site. So 80% of the power comes from nuclear power there. And as far as I know, there aren't people every day sort of demonstrating the streets of Paris against this evil business. So that's what you'd like your nuclear plants to look like. You could have it look something like this. This is how you don't want your nuclear plant to look, right? And you probably already know where this slide comes from. This is a recent occurrence. This is the Fukushima Daiichi plant that was subject to the tsunami, and what was that, a 20-meter wave or something came over this plant. So that's the kind of thing they ended up with. Clearly a disaster. I mean, nobody wants this. But as far as I can tell, there has been no one yet killed as a result of this. There's lots of discussion around about radiation and that kind of thing, but nobody was actually killed as a result of this. And as a result of the tsunami, generally, I think there are 25,000 people killed in the whole disaster. So clearly a huge disaster, but not where you want to put a nuclear plant in a seismic zone, so near to the water. Okay. That's enough, but we hopefully will have some questions and discussion about that afterwards. Let's talk a little bit more about sustainable transportation now and see if there is a possibility of it being more sustainable. And when I say transportation problem, it's really an energy problem. It's where do we get the energy to run our transportation? And at the moment, it essentially all comes from fossil fuels. You know, I'm not talking about you riding your bike to school. Everything else uses fossil fuels pretty much. So gasoline, diesel fuel, jet fuel to run things. And of course, there's no chance of capturing and storing the CO2 in any feasible way that I can think of for this. So if you're going to use transportation powered by fossil fuels, you're going to put CO2 up in the atmosphere. So we need to change what we're doing, which you might think of looks something like this. So this is my cartoon, and I hope there's no oil company folks in the room either, because I know this doesn't look like an oil refinery or anything here, but this is my cartoon. We take oil out of the ground. There's some emissions associated with that. And then this isn't Ford's latest SUV, but it's not far from it. You look at the size of some of the cars on the road today, right? So here's what we're doing today, and you can track the whole energy conversion chain along there. Well, maybe we should do something like this. So here's one prospect. We take a sustainable, renewable energy source here, so sunlight. In this case, we generate electricity. Then we take some water. We generate hydrogen by electrolyzing that water. We store the hydrogen, and we put it through a fuel cell on board this vehicle. We turn it back into electricity and drive a cute little fuel cell vehicle around. And I know if you're a car person, that's not a fuel cell vehicle, but it's a cute, efficient little car, right? So that's a sustainable approach to do it. And of course, there's been lots of interest here in B.C. about this on the hydrogen economy. We don't hear so much about the hydrogen economy anymore. And I think here's why. We could do exactly what we're doing in that other slide, but like this. Take the electricity and store it in a battery and then drive this vehicle. So all of this stuff, electricity, electrolysis, hydrogen storage, fuel cell, that's electricity coming in, it's electricity going out, it's a battery. That's all that is, right? So the whole hydrogen economy business is essentially giving you a very expensive version of a battery. Now, you can store, you know, the energy density is better here than here, but these are getting very much better. And so if you look at the overall efficiency of these, which you'd like to have very high, and I've done a comparison here of just what we call the in and out efficiency. What's the energy in, what's the energy out? And you go through each step in the chain for a hydrogen fuel cell vehicle, for example. Well, you're going to take your hard-won solar energy and you're going to turn that into electricity and electrolyze water, turn it into hydrogen. Well, that's about 75% efficiency. In other words, of the electricity you put in, the energy in the hydrogen out is about 75% of that. Then you've got to compress it. That's pretty efficient, so that's 90%. The fuel cell is at best 50% efficient. So it'll convert 50% of the energy in the hydrogen into electricity. So you multiply those together, so the overall efficiency, starting with your electricity going in to electricity out, is about 34%. If you store it in a battery, an electric battery, that's about a 90% efficiency. Batteries are very, very efficient in terms of just storing energy and getting it out again, right? So you would use something like 3 times the amount of primary energy over here going this route than going a battery route, right? So that's why we don't hear anything about the hydrogen highway anymore. And this is another reason, if you look at storage, energy storage on board a vehicle, of course, is also very important. Hydrogen is, you know, the lightest gas we have, and it's difficult to store. So you need to store it either at very high pressure, so you can store it at 350 bar pressure up here, here. And so to store, this is 5 kilograms of hydrogen. And so you would need, this is very approximate, that's why these points are very big. The weight would be something like 250 kilograms and a volume 500 liters just for the storage vessel, right? The 5 kilograms of hydrogen isn't anything compared to the weight of the storage you have. Or you can compress it even higher, 700 bar, something like 10,000 psi if you really want. And then you get it a little bit smaller, but it's very little lighter because you've got to have much higher wall thickness vessels. Or you could turn it into liquid hydrogen. That's still, you've got to have a container for that, and the volume's about the same as compressing it very high. Or you can put it in metal hydride. All these things have been sort of stock market darlings that people have talked about, you know. Well, the trouble with metal hydrides, it stores hydrogen at relatively low pressure, but you're carrying around all that metal. So you're going to carry 600 kilograms of that to store 5 kilograms of hydrogen. And then, if you look at that, oh, what's that down there? That's gasoline, right? That's why we like gasoline so much, or at least folks who like cars like gasoline so much. I mean, it's just so much nicer to store, so much easier to store. The energy density is so high in that. So that's the challenge for this. So hydrogen simply doesn't compete with electricity directly in the transportation business. And we really need a new energy carrier, not hydrogen, and we need to move to electricity. Now, this is actually happening as we speak. You're seeing more news every day about new electric vehicles coming on board. And so this is just a traditional little electric vehicle. We're starting to see those. The problem with those is the battery, again, doesn't store all that much energy. So your vehicle has limited range, and if you're in a very cold climate, that's a problem as well. You might want to have some heating and so on. So you have very limited range with this, and it might be all right for people who just commute back and forth to UBC, for example, but if you want to go and visit your grandmother on the weekend, that might be a problem. So the way to do that, I'm just sort of summarizing all that stuff here, the way to do that is have kind of the best of both worlds. And this is the so-called plug-in hybrid vehicle. And so you have the battery electric vehicle here, but then you also have an engine on board and some liquid fuel, some gasoline or diesel fuel. And the advantage of this is you can get maybe a range of 100 kilometers on the electricity you use here, which is enough for most commuters on a daily basis to commute back and forth to work. I think most folks here could do that easily and never have to have the engine come on. But when you want to go on holiday or you want to go longer distance, then the engine comes on just seamlessly, actually drives a generator typically, and the electric drivetrain takes forward. Now I put this slide together probably almost 10 years ago and was talking about this, and people didn't really know what I was talking about. This has actually happened much faster than I had envisaged. We're now seeing these cars, and you probably heard lots in the news about this. This is the Chevy Volt car now, which is, yeah?
Just curious, how many kilometers do you get once the batteries run out and the liquid fuel takes over?
Well, I mean, whatever a conventional car will do. You know, you can get several hundred kilometers.
So one like that car in particular is?
Well, I mean, that's just a schematic. So this is the Chevy Volt, but I can't tell you specifically about that. But the design would be to give you the same kind of range as you have with a conventional car. It might be 600 kilometers, something like that, right? So this is the Chevy Volt. It's got a 120 kilowatt electric motor here. It's got lithium-ion battery pack. It's pretty heavy, 16 kilowatt hours it stores. And then it's got a little 53 kilowatt diesel engine. They're more efficient, and that's small, and that comes on just to charge there's no mechanical drivetrain here. That simply charges the battery, and the control system, knows when the battery level is getting low enough and it has to come on. So that's what a plug-in hybrid vehicle looks like. Now, people say, well, gee, I've heard this. I don't want to plug in my car every night. What a pain that is. I've never really understood that argument. So let's parse that out a little bit. Well, if you had an electric vehicle and you're running on electricity, in BC we're paying 6 cents a kilowatt hour at home. There's about 10 kilowatt hours per liter of gasoline. So that's going to cost you 60 cents per liter of gasoline equivalent. That's the cost in energy equivalent. So you're going to fill up your car with 60 cents per liter equivalent. Well, that sounds pretty good. But it's even better than that, right? The electric car is about 3 times the efficiency. The efficiency of your internal combustion engine, your car, and I work in research on that area, so I know about this, is about 30% at best. Probably less than that on a drive cycle. And the battery is about 90% efficient. So you're going to pay something like 20 cents a liter of gasoline equivalent. And I don't think that's widely understood. I've started to see little snippets in the newspaper now, and people say, gosh, I got this electric car and I can't believe how little it's costing me to charge this thing up. So it's really a no-brainer from a cost perspective. So my answer to this, of course, is clearly people will be quite happy to plug them in. And if you don't, it doesn't matter. Then you'll burn gasoline and pay, 6 times the cost.
That's the weight of the car, adding the battery efficiency.
Yeah, I mean, the weight is high. I don't think I have data on that, but the weight is quite a bit. But the batteries are getting much, much better, and better than I ever thought. If you had lead-acid batteries, that's not very doable. That's kind of back to the old milk floats that they used to have in Britain, which I kind of remember But these batteries, you know, this vehicle, the Chevy Volt, will be a little heavier than a conventional car of that same size, but maybe, you know, 300-400 kilograms more, something like that.
What's the average lifespan of a battery like that?
Well, I think it's early days to say that. I talk to the taxi drivers around here all the time whenever I get a taxi who drive the Prius. They've all told me so far they've never had to change a battery. And I think they're saying 7 years, something like that. So that's an ongoing, you know, discussion. We'll have to see how long that lasts. What you want to do is take this material and recycle all that and use that in making new batteries, you know. Let me just try and sum up, and hopefully there's other questions as well. So we do clearly need to move to a low carbon future, and how do we get there? And I've just done some very crude guesstimates. I mean, that's what engineers like to do, these sort of, well, I like to do any back of the envelope kind of guesstimates before we get down and drill down into the details. So, you know, how long is it going to take us to go from here to here? Here's my kind of analogy of where we are and where we need to be, something like this, not just for vehicles, but for everything else. Well, it's probably going to take some time. And I've looked at a couple of scenarios, and I've just said, okay, we could have clean coal if the carbon sequestration is really going to work and people are happy to see it pumped underground. It's not going to come up again. Well, maybe we could go that way. Or we could rely primarily on nuclear and renewable energy. In either case, we'll be moving more to electricity as the favored carrier. Right? Electricity is used, you know, in a limited way at the moment, but if we do start to use it for all of our transportation, as I think we can do, or for much of it, then, you know, we'll move to an electricity economy as opposed to a hydrogen economy. So how might we do that? And here's just a quick summary of what I put together. There's no econometric modeling, nothing sophisticated in this. I just took the sort of growth projections. Here's real data up to here in terms of, this is world energy use, and so this represents oil, gas, and coal. There's the 80% of our energy that comes from fossil fuels, and then this little bit of nuclear here, and renewables. And this is primarily hydropower and the combustible renewables and waste. Combustible renewables, wood burning and so on, is a significant fraction of this. So here's where we were, and I just projected the total demand at going up at 2% a year, which is kind of where it's been going for some time, and then tailing off towards the end of the century down to, I think, 0.5% here. Population goes down and so on. But again, no sophisticated development. I just want to see roughly what we might be able to do. And then I made reasonable projections. If we went to clean coal, for example, how are we going to meet that? You see, there's clearly more than a doubling by the turn of the century, even at modest growth rates, of course, to get to there. Well, here's oil, might be gone by then, or we might be so tired of it that we stop using it. Gas, we're finding more and more gas all the time, so we'll probably still be using that. But I've projected, well, we'll probably use, you know, maybe twice what we're using now, but not a lot more. But we're using a lot of coal here, and we're pumping the CO2 underground, presumably, and paying a lot to put it down there. And then we're having reasonable increase in nuclear and reasonable in hydroelectric power. But look at this, we're still using, if we didn't sequester this coal, we're still, we would be producing much more CO2 than we're doing now by a long way. Or we could go to a nuclear and renewable scenario. So we say, well, coal isn't going to really, you know, be viable to store and capture all of this CO2. So yes, there'll be expansion in coal, but we'll keep it more or less where it is now. Gas will probably have the same as the last slide, oil almost gone, but a big expansion of nuclear power and a big expansion of renewable energy here, presumably mostly to drive electricity generators, and then we're using electricity for our transportation and pretty much everything else as well. But even in this scenario, we're still burning more fossil fuels than we are today. So these are the kind of challenges we have, even with the best of intention, I think. And you know, maybe we can do better than this, I don't know. But it seems to me unlikely if we follow this sort of trend of energy consumption. Of course, we should be using less energy. Okay, thank you very much. I'm going to end with a shameless piece of promotion. If you really want to know more, there's this wonderful book that you can find in a bookstore near to you. So let me stop there. Thanks very much. I've enjoyed the talk. I'm happy to take questions or have discussion.
just to help us with our future seminar series. I think, you know, to try to summarize, which is impossible, but I think one of the things that's obvious is the fact that we're going to continue using energy. And as the population continues to grow, at least for the next 50 or 60 years, we're going to be using more energy. Okay? And one of the things that always bothers me, and what's been very interesting here, is that in this part of the world, because we have so many sources, we are always saying, well, we don't want this, and we don't want that, and we don't want this. We don't want Site C, because Site C is going to increase the size of our reservoir, and therefore it's going to destroy more land. We don't want to frack, we don't want to do fracking, because that's going to cause water pollution. We don't want to develop our oil sands. We don't want to have more coal development and so on. And so I wonder where all this electricity is coming from. And the one thing that Bob didn't tell us is the fact that how we could capture lightning. Capture lightning and put it into a battery, we wouldn't have to worry about it. So it's a real interesting phenomenon. So I think what we really want to do is thank Bob for opening our eyes to the realities. And the fact is that you can't get something for nothing. So with that, if you would ask, I'm sure Bob would like to have something. Julie, do you know do something? Oh, okay. Oh, you're doing it. Thanks very much. Okay, Bob, any questions?
Yes.
You talked a lot about the improvement of coal use. Is there also work on gas use?
Improvement in coal use, yeah. I mean, even the improvements of coal use are not huge. You know, they help. There's not much improvement in terms of electricity generation from gas use, but it is still much better than coal. Because there's a very high hydrogen to carbon ratio in methane, which is the main constituent of natural gas. And because it is gas, you can burn it in this combined cycle approach. So any new power station that's built today using gas as a fuel is a combined cycle plant. So you have a gas turbine, which is ideally fueled by natural gas, and you take the exhaust from that and run a steam plant with that and generate steam. So you get much more use of the energy in there. So the CO2 production from a gas-fired electricity plant using that cycle is about half what it is from a big coal-fired plant. So that's why I think, you know, with this fracking and all the new gas we're finding, there's going to be a much greater move towards gas-fired plants. And I think we've seen that in China and other parts of the world. And I don't think in the US we'll be building more coal-fired plants than building gas-fired plants.
In your scenario, the coal-fired plants would go up, and I was just wondering why not the gas? Like, why do you think people would use more coal but not really more gas?
Oh, in my coal scenario?
Yeah.
Well, in that scenario, I'm assuming they're going to store the CO2 underground. But I mean, I think that's probably not a terribly viable scenario. Probably should have a bigger gas. Yeah, so I take your point from that. Yeah.
I think you had another question, wasn't it, Carmen? Why are we still using coal when we could be using gas?
Yeah.
Well, it traditionally has been very cheap. It's still very cheap. And depending where you are, I mean, China has an awful lot of coal and not so much gas. And we're trying to sell them gas, I guess, if we ever get to build a pipeline and terminals and all that, we'd love to sell them some gas. But they have a lot of coal. And I think pretty much many places in the world have coal. Americans have tons of coal. We have a lot of coal. So it's widely available and it's very cheap. And it's just been traditionally used. I mean, that's where, most of Europe got all its electricity till not that long ago.
Maddie and then Julie.
Okay, good.
When you plug the car in,
yeah.
How much does it raise your electricity bill?
Well, sure, you have to pay for electricity.
Yeah. So how much does it raise it?
Well, I can't tell you exactly how much. It depends how much your electricity bill is.
Right.
But not very much. I mean, it's very little. I mean, it's about maybe a fifth of what your gasoline bill is.
Right.
Something like that. Okay, so you add that on your electricity bill.
I have a question from one of our webinar participants. Dr. Evans, can you estimate the electricity requirements for a complete move from ICE to complete electric vehicles in BC and or North America?
No is the short answer to that. Given a bit more time, I think I could. But again, what you need to do is take how much gasoline we're using today. Say all the vehicles are gasoline. We want to switch them all to electricity. and divide the energy by roughly 5, something like that. And that's what you, maybe by 3, divide it by 3, because of the much higher efficiency of the electric drivetrain, and that would give you the result. So I can't do that on the spot, but that can be easily done.
Julie?
I have a personal question.
Sure.
I am interested to know how the availability of water factors into your future scenarios, and if we're expecting that fossil fuels are going to go down from the 80% that they constitute now, if they're going to decrease, or if we're going to switch to renewables or nuclear. Do you know anything about how the availability of water is going to factor into feasibility and sustainability of the new energy picture?
Actually, no is the answer to that again. I'm not sure, are you meaning water for hydropower development in particular, or?
Water for nuclear development, and how does water factor into the operation?
Yeah, I mean, water, you know, water is used in all these big plants, but it's recycled water. You know, there's always a little bit of water used, but I mean, the steam is completely recycled in a power plant, right? So the steam is condensed back in the water, and that's pumped back into the boiler and boiled again. They need to be on a big source of water to get cooling water, so they have to cool the plant. And there's a little bit goes up in those cooling towers. There's a very small fraction of water actually goes up in the atmosphere, but you know, water is completely recycled, I think.
But also for fossil fuel extraction, there's a large amount of water that's required for a lot of.
I think it depends very much on the process, right? You may know much more about that than I do. I'm certainly not an expert in that. Yeah.
I'm curious if you've looked at any scenarios around radical demand side changes, transitions there, and how that would affect, so, you know, sort of our aiming weapons and soft path type stuff. And if not, why not?
Okay, well, no, I haven't. But it does take me back 30-some years ago. I actually worked for the provincial government here and ran the first energy conservation program. And we were trying to get people, encourage people to do better and conserve and use energy more efficiently. Almost nothing happened. And 30 years later, I'm looking back, and there have been small changes and small improvements and so on, but almost nothing has happened. So I'm not a psychologist. I can't, you know, suggest how people's behavior might change. It's clearly an important issue. And I didn't talk about that in this talk. It was more a supply side talk, but there's a whole issue of demand side management. And there's lots of stuff we can do technically, but at the end of the day, it's a people thing. And if everybody finally decides to use energy more efficiently and less, then that will have a big
It's also
impact.
political though, right, as well. This is, I think, so I look at demand side stuff and planning.
Well, if it's people, it's political, right?
But and so just as decisions around what fuel sources we're going to use, it's also around demand. So BC Hydro, for example, did a 20-year different scenarios, demand scenarios, and looking at, so they call it bending the curve on demand, right? So if they could actually by 2027 get back to the demand levels that we are now, and they did these 4 different scenarios. And one of them said, okay, if these policies are put in place, and basically what it is put a big shift from utility demand side management to government policies. And then they said, yeah, it's possible that we could bend that, right? And so this is why I'm curious if you looked at a scenario, because I think, so someone like Mark Jackard often gives the argument, well, it's path dependence, and we can't change these things, and these are what people want to do, and it's also, it's path dependence, but it's based on decisions that are made, right? That needs to be in. So I think it's demand scenarios, as much as it's hard to change that, they shouldn't be ruled out.
No. I certainly wouldn't rule them out. I just think it's very, very hard work to have that bend down, particularly electricity, because I do think we're going to move more to electricity use as a carrier. So as we switch our transportation to electricity, the demand is going to continue for electricity. But that's okay if we're getting rid of fossil fuels, I think. Much better to move to sustainable electricity generation and away from fossil fuels, it seems to me. But I mean, no, I'm not an expert in demand side management. There is a huge issue there. But not, you know, it does involve changing everybody's mind about these things.
Yeah, or getting enough political will to...
Political will, but that depends on changing enough people's mind, right? You've got to be voted by the majority of folks, so, but I'm way outside my area of expertise. The only thing I always say to students, they ask me this kind of question as well. I remember, you know, I'm old enough to remember blue box recycling when this first came in. I'm an old geezer. My kids say, Dad, you got to recycle those newspapers. Yeah, I've never done that. What do I want to do that for? And now I'm, one of the biggest recyclers around, recycling everything. So even folks like me can change our behavior patterns in maybe a minor way. So I guess if I can do it, then there's hope for us. Yeah, right? So, we're learning from the younger people all the time.
Carmen?
I was just thinking, you said that people say like, oh, I didn't want to plug in my car.
Yeah.
And when I think about electric cars, I think that, well, I personally wouldn't have a problem plugging in my car. There are people in the interior where it's super cold and they anyways have to plug in their car. But I think about, wow, how long does it take to charge it actually? So what are the numbers right now, and where do you think can we get? Because I see that as a major problem, that people don't want to go on a trip from here to Okanagan and then have to stop every time for 6 hours.
Yeah, and I don't think, people are, even people get excited by, well, we've got charging stations now in Vancouver, we've got a charging station. I think that's a red herring, frankly. I think the way the vehicles are going, you're not going to want to charge them up during the day, unless, you're a commuter and you park in a company parking lot or something. You park at UBC every day, you could do that if UBC will pay for the power. But for most commuters, you'll be able to plug it in at night. And to answer the question, probably 8 hours is what it takes for a full charge at 120 volts. If you put a 240 volt system in, which is relatively straightforward, you can cut that probably in half. So most people who are commuters would do that overnight. So you wouldn't ever need to plug it in at a charging station, very unlikely. But again, if we, we won't be going very much to pure electric cars. I think we will be going to these plug-in hybrids. And so you still will use a little bit of fossil fuel, but it'll be a very small fraction. It's only for when you want to go to the Okanagan or longer trips, right? You'll do that. So for commuters, you plug it in at night. I mean, the other ideal thing about that for utilities, utilities love the idea of electric cars because it helps their load factor, right? So the electricity load is very low at night. And it's not so important here where we have a hydro system, but if you have a fossil fuel fired system, you want to run those plants all the time. So you'd like to have load leveling. So you want your demand to go down during the day and you want it up at night, for example. And that's what plugging in electric cars in the millions will do. So it will improve the load factors for utilities and ultimately bring the cost of electricity down from what it would have otherwise been. So I gave this talk down in California quite a few years ago, and the guy got up and said he was the head of the electricity regulation group there, and they just couldn't wait for electric cars to come in because the utilities love that load leveling. Yeah.
There was some research done a couple of years ago in southern Arizona that said that there's enough, I don't know the specifics exactly, but there's enough solar energy in southern Arizona to power a vast amount of the United States. Yeah. Do you know, or could you explain to us a little bit about the costs associated with transporting that energy from, say, if we actually produce all the United States power in southern Arizona? Is it solely through power lines that power would be transferred to Washington?
Principally, it would be electricity generation, almost certainly, if you use. And there, you can find somewhere you can find a map which shows the area of Arizona that will be required to power all of the United States, and it's not the whole state, So that can be done. And you may have seen there's some really interesting schemes for Europe that show much of the Sahara covered in solar panels, and then subsea cables going to Europe. And these sound a little far-fetched, but down the road, maybe that's what will happen. So that's all doable. Photovoltaic cells are expensive. They're coming down. They're expensive, and then you've got to keep them clean, and there's all these sorts of issues, which I'm sure can all be overcome. But the cost is coming down. But they are very expensive, and of course they're intermittent. So you again get back to the storage issue. So there are folks working on all of that. Yeah. So it's not an issue that we don't have enough energy from the sun. We've got plenty of energy from the sun. It's the cost of it and the efficiency of capturing that and trying to store it and use it when we want it is the big issue. Yep.
Over any questions?
Great. Well, thank you very much. I enjoyed it. Yeah, thanks for your questions. Yeah, thank you.